Alright, in this example we want to compute the arc length of a cardioid. We could use any formula for a cardioid that we want because the different orientations won't change the arc length. But in the example in the notes we're asked to find the arc length of the cardioid, whose formula is r of theta equals cosine of theta plus 1. So you could at this point sketch the cardioid, maybe graph it on a computer or a calculator just to get a look at what you're working with. But it's not really required of us because in the last video we derived a formula for the arc length element, and that arc length element was given to us as by this formula. We derived it. It wasn't given to us, but we worked it out. This is going to be equal to rho dot squared plus rho squared d theta. And what the heck is rho? Well, this is where r is equal to rho of theta. So in this example, the way this is written here, the rho, that's the function that is determined, that is our polar function, the equation of our polar function. So the cosine theta plus 1. So what we need to do first is work out what this arc length element is. Then we can write down the integral, and once we have the integral, I'll let you guys compute that part on your own. But let's work out the arc length element. So we need rho squared. So before we actually take any derivatives, let's just square it. So rho itself, remember, is the formula for the function. So cosine theta plus 1, quantity squared. And this, of course, has to be distributed out. So this is cosine squared theta plus 2 cosine of theta plus 1. And then we need rho dot squared. But of course, before you can square something, a rho dot, you have to actually compute rho dot. So rho dot is the derivative of the equation with respect to theta. That's going to give us a minus sine of theta plus 0, so just sine of theta. And so rho dot squared is just going to be sine squared theta. And I'm going to write that over here because the next step is to add these two up. And as we see here, if we add these two, that's a Pythagorean theorem. And what we end up with is that our rho dot squared plus rho squared is equal to, this is a 1, plus 2 cosine of theta plus another 1. Alright, so combining this all together, we find that our ds, our arc length element, is equal to, remember you have to take the square root of this, so it's the square root of 2 plus 2 cosine of theta d theta. So this is the integrand, or really this is a differential, but this is what needs to be integrated. We need to integrate this around the entire cardioid, and you can go back and review our cardioid lecture if you want, but the cardioid is traced out as theta goes or varies from 0 to 2 pi. And so what we end up with, I'll write on the next page, our integral is going to be the integral from 0 to 2 pi of this. That's it. That's the arc length. So here's what we get. Our arc length of the cardioid is the integral from 0 to 2 pi of the square root 2 plus 2 cosine of theta d theta. Alright, now I'm going to let you guys integrate this, but I just want to remind you that this integrand is a little bit tricky, or can be a little bit tricky, but you've seen this one before. So this one showed up when we tried to find the arc length, sorry, wrong button, when we tried to find the arc length of the cycloid. So this integrand looks very similar to the cycloid's arc length. Alright, and in that video we talk about a trick of how to deal with this. So just looking at this, again, I'm not going to work this out for you in this video. I want you to try to do this yourself. But one thing you do is you can factor out this square root 2, and you're left with something like this. And what I want you to do is think about, if you take this out of the root for a minute, can you find a trig identity for something involving 1 plus cosine of theta? And I'll give you a hint, in the process you might have to change the theta itself.